Folks, thank you very much for sticking around until the last talk in what's been a very intense session. We started with, really fun tweet visualizations in politics to catching sex traffickers and dealing with the Flint water tragedy. My talk's going to be a little different. I'm from Google Research. My name is Sandeep Tata, and I'm going to be talking to you guys about some of the work we did with folks in Google Drive and try and tell you about some fun lessons and interesting things we learned from this experience of deploying an end-to-end machine learning system. So before I get started, there was a study a few years ago from McKinsey Global Institute where they said that knowledge workers spend about 19% of their work week just looking for the right document or piece of information. 23% of the time is spent on checking email, and I see some of you are still dealing with that. So if you add that up, it's about 40%, and the real work doesn't begin until Wednesday on a normal work week, right? So some of us in research teamed up with folks in Drive to try and figure out if we could start making a dent in this problem and improve the world's productivity, right? I'm happy to report that we've made some progress. I'm going to talk about a feature called Quick Access in Drive, which gets you to your files about 50% faster than we used to before. But of course, this is not going to put a big dent in the email part. This is just the first part. We'll talk about email in different papers. Okay. So for those of you that are not familiar with Google Drive, Drive's a storage and collaboration service that's used by several hundred million people in the world. So the storage part, I think most of you know about. If you could create files or upload files to the Drive service and access those files from any device in any part of the world, so long as you have an internet connection. Drive's also a collaboration service. And what that means is you have a document, you could share it with a bunch of other people, and your collaborators can sort of offer suggestions on the document or try and offer comments on the document, and you can sort of accept those suggestions, let others edit the document. So you can work on a document with a whole bunch of other people, right? And what we did in collaboration with Drive is this feature called Quick Access, which surfaces what we think are the most relevant documents that you're looking for right when you visit the Drive home screen, right? And we do this by learning a machine learned model on both the activity that you have in Drive as well as your context. What's on your calendar, what time of day it is, are you at home or elsewhere, stuff like that. So here's what I'm going to try and do for the rest of the talk, right? I'll tell you a little bit about how we built this. But mostly, I want to use our experience as a vehicle to sort of summarize a bunch of interesting challenges that we faced when building sort of a production-scale, end-to-end machine learned model that faces hundreds of millions of users. And I think there'll be interesting takeaways for a lot of people that are practitioners. And I'll try and conclude with sort of a call for interesting research that would help a lot of people in industry sort of execute on bringing machine learning to lots of products. So getting people to the documents in half the time, it's probably going to look like saving just a few seconds or a few minutes every day. But because we serve hundreds of millions of users across the world, this adds up to sort of several work months worth of time saved pretty much every day. So it's actually very gratifying to see that we're making a dent in sort of knowledge workers' productivity. Okay, the first part, how did we build this? Let me give you a brief overview of sort of the infrastructure that goes into building a product like this, right? So we'll start at the bottom of the slide. You see two boxes, one's called Activity Service and one's called Calendar and User Metadata Service. So the Activity Service is a service built by a different team outside of research. And what they basically do is gather all the data that's associated with all your activity in Drive, right? So you edited document D1 at time T1 on your laptop. You posted a comment on document D2 on a phone at some other time. So it sort of gathers all this information that's logged and makes it available in a big dump so you could do analytics or learn models over it, right? And there's similar dumps from other services such as calendar and other user metadata like how long have you been on Drive, how many files do you have in Drive, stuff like that. The data from these two sources is joined, and we produce training data. I'll talk a little bit about how we're modeling this and how we're training this. You run this through some tool. We used Brain and TensorFlow, and you produce a model. This model is loaded into a prediction server. That's the right side of the slide. And as traffic's coming in from clients to the Drive API, it makes a call to the prediction server, which in turn makes a request to either the activity service or one of these services to get real-time sort of features about what's going on, right? So when you're actually serving the model, you're making a call out to some service that gives you a bunch of data, recent context or recent events, and then you feed that into the model and make your predictions. This is going to be interesting. I've drawn the two lines in bold there to make a point later on, but this is sort of the general setup. Okay, I'll talk a little bit about the modeling, but the big point to notice first off is that in Drive, the corpus is actually not a public corpus, right? So it's not like YouTube recommendation where there's a big pool of videos that you're trying to recommend and sort of bring the most relevant videos as soon as you visit the homepage, right? A large number of documents in Drive are completely private. Only one person sees them. There are a bunch of documents that are shared with a small group or just a small number of users, and there are other documents that are shared with a large number of users across the whole company, right? So very different from sort of a public corpus recommendation system. So the way we model this is as a binary classification problem, right? Take a look at all the documents that people opened. So each of the opens is a scenario. And every time somebody opened a document, you treat the open document as a positive example and all the other documents as a negative example. You simply learn a binary classifier. And then at runtime, you're going to use the binary classifier to produce a score and rank order the documents and present it in that order. A couple of interesting details. Because it's a private corpus, you're not going to try and learn sort of an embedding for a doc ID, because you're not going to try and use a doc ID. It doesn't make a lot of sense. Instead, what we do is represent each of these documents along with the context, and I'll talk a little bit about what context means, as a feature vector, right? And I'll go into some details on how you would represent this. So not learning an embedding for a doc ID, we're not going to use the identifier as a feature, but represent what we know about the document and the context as a feature vector, and sort of do your scoring and ranking over those feature vectors. So if you have a corpus, and for simplicity reasons, we sort of limit the corpus to any document that has activity in the last 60 days. There's more details in the paper about why that's a good decision. So for example, if you have a corpus with 10 documents, D0 through D9, you open D3 and D7 at some times, we're going to produce two scenarios with 10 examples each. And in the first scenario, we're going to have negative examples for everything but D3. In the second scenario, we're going to have negative examples for everything but D7. And we're going to have feature vectors for D3 and D7 with context variables associated with the time in which you opened the document there. Okay? Very simple setup. Now, let me tell you a little bit about what these feature vectors actually look like. So we pulled in a whole bunch of different data sources to actually compute these feature vectors. One example is what we call sort of an activity fingerprint, right? A very simple way of representing a complex time series, right? So there's a whole bunch of different types of events that Drive tracks, right? You may have just opened a document or edited a document or commented on a document or renamed a document or trashed a document or untrashed a document. So a very simple activity fingerprint is if you're just doing a fingerprint of all the open activity, like when did you open or view this document, just represent time in sort of at some granularity of buckets. And for example, in this case, if you had D1 that was opened at T minus 20 minutes and T minus 40 minutes, D2 at T minus 100 minutes, and you're using your 30-minute buckets as far as 3 hours of history, then one possible way of representing this would be, D1 will have 1 and 1 for the first and second buckets and zeros in the rest of the buckets. D2 will have a 1 in the fourth bucket and zeros in the rest of the bucket. So, very simple representation of a time series. You're going to see why I'm building up to this. There's a whole bunch of other classes of features that we use: frequency ranks, recency ranks, document features like one-hot representation over a vocabulary of MIME types, and a whole bunch of context features like what time of day was this, what was on your calendar in terms of meetings, or who were you meeting with in terms of content of the meeting and stuff like that. Is there an overlap between the people on the document and people in a meeting? User level aggregates, like do you tend to look at a lot of docs or presentations or pictures, stuff like that, right? So each of these features, we sort of did shallow feature engineering, took a very simple representation and built it into this feature vector. The tool we ended up using to actually learn a classifier was a feed-forward network with a stack of ReLU units. Now, you may notice that this is not an obvious choice, right? So the data that we're feeding in is from a structured log. So it's not images or speech or voice. So it's not obvious why we would pick deep networks. We did this for several reasons. One is we wanted to understand this hybrid approach where we did sort of shallow feature engineering. We built a large number of very simple features, and we rely on the deep network to sort of figure out all the interactions. And two, we have really, really great tooling around deep networks, so we thought it would work. It would be a good opportunity to exploit that. And we had tons of data, so that tends to be an operating point at which deep networks work really well. So the hybrid approach we were doing is instead of relying on the deep network and doing a lot of architecture engineering, where you're sort of trying to understand a very interesting architecture or network topology, we did lots of shallow feature engineering and sort of relied on the deep network to do a good job picking up all the interactions there. So we have a very simple networks, a stack of ReLUs, what worked really well. So we explored a whole bunch of different hyperparameters. The width and the number of hidden layers, what sorts of activation functions we should be using, different types of initialization strategies, different learning methods, as well as various levels of learning rates. There's details in the paper about what worked out really well, but an interesting point to take away was in this setup, which is sort of a mixture of traditional feature engineering plus sort of relying on deep networks, we did find that sort of throwing more energy into quickly pulling out more shallow features out of what would be a log record or an activity record with several thousand tail fields was giving us lots of benefits very quickly as compared to doing very clever hyperparameter or network optimization. So there's a lot of mileage you can get from shallow feature engineering and combining that with deep networks. Okay, we're not doing some fancier models that might help us in the future. We're not doing pairwise. Even though we're solving a ranking problem, we're using just a simple classification approach, and we got very good mileage from that. We're not doing document embeddings or sort of RNNs at this point. Okay, so how well did this work? So we got really good results pretty quickly. So as you might imagine, because of the temporal nature of our activities, the most recently used heuristic is a pretty powerful baseline. In fact, for some of our initial simple models, we're not able to beat the MRU. But once we threw in enough features, we had substantial improvements in both CTR, as well as sort of the top 3 accuracy and average click position over MRU. The interesting and rather gratifying takeaway is that the improvement that the learned model gives you over MRU is much greater for active users compared to sort of light users, right? If you reflect on that for a moment, that's not very surprising. Active users have much larger working sets, and there's a lot more data about them, so the model's actually learning something about the preferences of these users, rather than people who have like 4 or 5 documents and you go back there all the time, in which case MRU is probably reasonably good, right? So it was really good to see that people that actually have large corpuses and have interesting access patterns are getting help the most compared to sort of a simple but effective MRU baseline. There's lots of details in the paper about the sort of performance and how we compared with different slices of users, but I'm going to switch gears a little bit and talk about 3 really interesting challenges that we encountered and some lessons that we learned from that. Okay, so the first interesting challenge is protecting user privacy, right? So Google takes user privacy very seriously. And what this means is if you're building a machine learning model or trying to build an intelligent feature, there's a lot of thought into making sure none of the data gets leaked, no human ever inspects any of these logs. As a result, any machine learning feature that's built over private data ends up taking a lot longer than a machine learning feature that's built over sort of a public data set like a web crawl, right? One of the things that we had to do is a bunch of steps that pretty much everybody does when you start an applied ML project, right? An exploratory data analysis, you do some data cleaning, you get an intuition for the data, you try and understand what fields are missing. But you can't do this with human inspection. So one of the examples, this is probably best explained with a little story. One of the things that we ran into when we first built this product was before we launched it, we saw we had really terrible predictive performance on a small slice of users. And one of the ways in which we could characterize this slice was that the previous document or document and drive that they had viewed was only a few milliseconds before this particular scenario. And there was a big slice of users where the previous document was about 20 or 30 milliseconds before this current view. And that looked very strange, right? How many people are actually viewing a bunch of different documents 30 or 40 milliseconds apart? When we try and got my colleagues to donate the data so we could look in the logs and see, is this really happening? Is this a logging error? Or is there something that's logging these opens multiple times? Or there are two systems logging this just a few milliseconds apart, and they're just appearing, the same opens appearing as two different opens. This was incredibly frustrating to debug, simply because we couldn't get an actual log to look at. When we had people in the team donate data, this didn't show up in any of the people that actually donated the data, right? I see some of you nodding in the audience, so some of you have run into these sorts of problems before. We eventually figured out what was going on. It took a lot of pain. Turned out that some people look at a lot of photos in Google Drive. Googlers tend to use the Photos app, which is really cool. If you haven't used it, you should check it out. As a result, none of the engineers had this behavior of looking at Drive and looking at a bunch of photos in Drive. And if you were swiping through a bunch of photos, there was a prefetcher working to sort of bring in all the documents, and that was logging a bunch of opens. So there were false opens, even though from just prefetches instead of actually displaying opens, right? So this took an enormous amount of energy to figure out when you can't look at anything in the logs directly. So if you're working on private data, plan for more time. And I'm gonna wrap up with some call for interesting research in this space. The second question, which I think is the second challenge which we encountered was what's called train serve skew. So if you went to some of the other talks from my colleagues at Google yesterday, and even some of the talks from folks in the industry at the invited talk session, you would have heard something about train serve skew, which is a very simple idea. The model sees different data when you're actually serving predictions compared to the data that you actually trained on. This happens a surprisingly large number of times in actual practice. And the reasons for it are always very convincing and meaningful after the fact, right? One of the examples was when we actually made a call to activity service from the prediction server, it was very helpfully renaming a lot of the event classes. So we have 6 different types of comment events, right? You could just add a comment or resolve a comment or reply to a comment, and there's a few more. But because the activity service was not built for a machine learning product, right? This was a team that already existed. They were already gathering this data. They had helpfully sort of collapsed all these comment subtypes into a single comment class because they're using this in a UX element in Drive, right? So when we actually ran the model, we saw completely different performance than what we'd predicted online. And we're very interested in sort of systematic approaches to guard against train serve skew and protect yourself against these sorts of things. One of the somewhat controversial arguments that we're proposing in the paper is if there's a mechanism by which you could get a data dump for a user-facing product, don't be tempted to use it. Instead of getting the data dump for a user-facing product, go gather your own data by instrumenting the serving stack and doing a dark launch in the beginning. So if you're going to serve something in production, instrument that first, because there are 4 or 5 different ways in which we saw the data differed from what was actually in the dump. If it said there's data at timestamp t, that may not have been available until t plus delta, and those sorts of effects you don't see unless you actually gather the data from a running system instead of a dump. Okay, challenge 3, which is probably familiar with everybody who's worked with a significant UX component, is the challenges to machine learning from an evolving product definition are very interesting. And if you don't involve your UX team early on, you're going to learn this in a very unpleasant way. So our initial mission was, we have all this interesting data. We want to help users get to their data faster. What product should we build, right? We thought of many things. We're a search company initially, so we thought as soon as you go to the search box, we'll try and suggest the right documents. We realized pretty soon that this means people who only navigate, not search, but sort of click through folders in Drive will not get helped by this, right? So we discarded that. The modeling for that problem is completely different. The data you want to gather is completely different compared to the one that we actually ended up solving, right? The next, we considered another approach where if we had a high confidence prediction, we would just do a little pop-up and say, hey, is this the file you're really looking for? And studies showed that if you actually do an intervention of that sort, people are likely to get annoyed when you get it wrong. And when you don't get it right, or when you don't trigger a notification, people are concerned that things are broken on their system. This is something that as sort of a machine learning person, you're not going to know unless you sort of work with UX and user research to sort of understand what are the implications of the ways in which you're surfacing your data. And so we finally ended up with what looks like this, which is what, if you guys use Drive on either your mobile phone or on web, you will see. OK, I'm going to quickly talk about one more little story and then wrap up with a call for sort of interesting areas of work, right? So the first thing that we saw when we actually launched was our top 3 accuracy was really good, like some number X, but the actual rate at which people were clicking on our predictions was close to half of X, right? Which means we got the machine learning right. We were predicting the right documents and showing this to you at the top third of the screen, right? Either on web or on the phone, but people weren't clicking it. Instead, they sort of scrolled through and then eventually clicked the same document that we showed you at the top third of the screen. This was very puzzling for a while. After a little bit of research, turned up there were 2 very interesting reasons for this. The first one was, of course, latency. Let's skip that. Which is, the longer it took to show the actual prediction, if you saw a little spinny wheel where we were trying to fetch the icon and the actual document, people got tired and sort of scrolled through and actually clicked the same document from a different part of the UX. And so as we started improving the latency of the backend services, we saw dramatic improvements in the engagement rate, like how often people were actually using the predictions we were surfacing without any improvements in accuracy at that point, right? So this was super interesting. So don't forget your actual engineering in the backend. The second part was a very simple visual change, right? At launch, we had the UX on the left, which was just a little icon for the file type and the title. And when we switched to actually using images from the files, we saw the engagement shoot up. So again, the lesson being, don't forget to engage UX early on, because even if you get all the machine learning right, if you don't get the UX right, you'll have great accuracy metrics, but not quite the right engagement metrics. OK, with that, I'm going to wrap up by calling out sort of 3 areas of work that I think will be incredibly beneficial to really bringing the power of machine learning to tons and tons of products around the industry, right? The first one is improvements in algorithms and tools at the intersection of both data cleaning and feature engineering on private data. What tools and techniques can we bring to bear here that will speed up how fast we can deliver interesting machine learning over private data? The second one, of course, is a systemic way to guard against train, serve, skew. There's a bunch of approaches that we've written about in different papers. And in our paper, we talk about this dark launch and gather your own data first approach. but we're very interested in more systemic approaches to sort of ensure against these sorts of problems. And the third one is one of my favorites, which is the sort of hybrid approach where you do a bunch of shallow feature engineering and leverage deep networks to sort of help you out there. So more work about how to deal with structured data and feature engineering and sort of representation of structured data for DNNs would really help unleash the power of what we've been learning on DNNs on a whole wider set of problems than we do today. And with that, I thank you very much for your attention. Coffee is only a few questions away. So
great. Let's thank our speaker.